Alright, we'll continue with section 14.9, and now we're going to talk about surface area. So if S is a smooth parametric surface given by R of uv equals the vector x of uv, comma y of uv, comma z of uv, where S is traced out exactly once as uv varies through the planar region R. Then the surface area of S is area of S equals the double integral over the region R of the magnitude of RU cross RV dA. So to find the surface area, we'll have to find, sometimes we actually might have to find our parametrization ourselves. So you might have to find the parametrization, then take its partials with respect to U and V, then take the cross product of those partials, then take the magnitude of that, and then sketch your region R, or you might sketch your region R earlier, but sketch your region R to set up your iterated integral and evaluate that. So it's a lengthy process. So there's one scenario, well not, or a few scenarios where we can save ourselves some trouble, but I just caution you to not try to use this all the time, which a lot of times people do. So in the event we can use our favorite parametrization x equals x, y equals y, z equals f of x, y. Actually, I'm going to put this in parentheses so people don't think that you can use this all the time. You can only use what I'm going to give you if you have this parametrization, which we usually don't have this, but if we do have it, a lot of the work's been done for us. So in the event, we can use our favorite parametrization. For R. The magnitude of R sub x now, because our parameters are x and y. The magnitude of R sub x cross R sub y equals the square root of f sub x squared plus f sub y squared plus 1. Actually, we'll just leave that there. I was going to say has already been computed for us, but it's better for me to just leave it at that. So if that's only for this parametrization, if you are able to use this parametrization for whatever your surface is, then you don't have to go through all of those steps. They've already been done for you. And this was done on page 9 983 on the text, 983 in the textbook. So see pages 983 to 984. They already did all the computations for you in the event this is your parameterization, but it only works for that parameterization. So every time I teach, I oftentimes see students try to use this for every single surface area problem, but there is no F in up here. So there's no way to try to use this for in this scenario. You can use it in that scenario, and that's the only time you can do it. And there's a similar setup that you can easily kind of decipher from if you had, say, for instance, x equals x, y equals a function of x and z equals z. Then these partials down here, the partials are always going to be with respect to whatever your parameters are. So x and y, if the parameters in the parameterization similar to this one happen to be x and z, then this will be x and z. But it's only for when you're using your variables x, y, or z as your parameters, and then the other one is just a function. So this is that scenario where you could solve for x, y, or z in whatever equation you're given. All right, so now let's look at a problem. And this problem is not going to fit on this page, so let's go to the next page. All right, so we're going to look at number 22 on page 985. So number 22 says, in exercises 22 through 24, find the area S of the surface sigma. And they say sigma is the portion of the sphere r equals 2 sine phi cosine theta. Oh, so they're giving us our vector function. So this is r of, now our parameters here are theta and phi. So r of theta comma phi equals a vector. Let's see if I can fit this on one line. So the I component is 2 sine phi cosine theta. 2 sine phi cosine theta. The J component is 2 sine phi sine theta. 2 sine phi sine theta. And the K component is 2 cosine phi. All right. So they give us that, and they say that lies above the plane z equals 1. So it's the portion of that lies above the plane z equals 1. All right, so first off, just to find surface area, we're going to need to find r sub phi, and they give us a hint. What are the ranges of phi and theta? So that hint is basically telling us that we have to find our region R. So I'm not quite sure how that hint is supposed to be helpful. You're going to have to do that for any problem that you do, where you're going to have to find surface area, whatever your parameters are. You're going to have to find the bounds for your parameters, because the bounds for your parameters give you the bounds for the double integral. All right, so now we're going to need the partial of r with respect to phi, partial of r with respect to theta, cross product those two partials, and the magnitude of that cross product. Then from there, we're going to have to put that in a double integral and set up that iterated integral and evaluate. Excuse me, I don't know why I can't talk. All right, so now r sub phi, we'll start with that one, equals the partial of each one of these with respect to phi. So the first one, cosine theta, and 2, those aren't going anywhere. And the derivative of sine phi is just cosine phi. So we're going to get 2 cosine phi cosine theta. And then the partial of this with respect to phi is 2 cosine phi sine theta. And the partial of this with respect to phi is negative 2 sine phi. Now, r sub theta equals, the partial of this with respect to theta is negative 2 sine phi sine theta. partial of this with respect to theta is 2 sine phi cosine theta. And the partial of this with respect to theta is just 0. All right, so now we have those. We need to compute the cross product. So r sub phi cross r sub theta, and it doesn't matter the order in which you compute this product, because we're going to end up taking the magnitude of it anyway. So whichever way you compute it, the magnitude is going to be the same if you compute it the opposite of the way that I'm doing it. So this equals, I'm going to write these in first because they're going to take up some space, and then I'll put the I, J, and K at the top. So we have 2 cosine phi cosine theta, 2 cosine phi sine theta, and then negative 2 sine phi. And then down here, negative 2 sine phi sine theta, 2 sine phi cosine theta, 0, I, J, K. Make sure I copied everything down correctly. 2 cosine phi cosine theta, negative 2 sine phi sine theta, 2 cosine phi sine theta, 2 sine phi cosine theta, negative 2. Okay. All right, so now we're computing this cross product. We get this equals, this is going to take up some space as well. So this equals, so ignoring that, we just get 0, then minus negative. So we're going to get 4 times sine squared phi cosine theta. Let me see if this will save me some space. 4 sine squared phi times cosine theta. And then ignoring this, we're going to get 0, and then minus 4 sine squared phi sine theta. But then we're going to have another minus sign, so we're going to get a negative right there. Is that right? Let me make sure I didn't mess up my signs. This is 0, and then minus that. So that was a negative. So actually we're going to end up with positive. I think I was about to put negative. One more time, 0. That's positive. There was a minus sign in front of that already, negative, plus our negative. So we are positive still. All right, so what did I say? 4 sine squared phi sine theta. 4 sine squared phi sine theta. And then lastly, let's see if I can fit this in here. We're going to have 4 cosine phi sine phi cosine squared theta. And what are we going to have here? So I can try to simplify this. Minus, and then the negative 4. So nothing squared. Oh, sine phi cosine phi sine squared theta. So we have the same thing there. Let's see. 4 cosine phi sine phi, and here 4 cosine phi sine phi. Yeah, so we can factor that out. So 4 cosine phi sine phi, and here from the 4 cosine phi, from those two terms, we were left with a cosine squared theta. So it's a cosine squared theta. And then here, this was minus a negative, so it's plus. When we factor out the 4 cosine phi sine theta, we're left with sine squared theta. So plus sine squared theta, close that, and close our vector bracket. All right, so now this, of course, in parentheses is just 1. So we end up with these three terms right here. And then we need to find the magnitude of that cross product. So the magnitude of r sub phi cross r sub theta is equal to the square root of this square plus that square plus that square. So this equals, put this on the next line. This equals the square root of this square, which gives us 16 sine to the fourth cosine squared, 16 sine squared of phi, 16 sine to the fourth of phi cosine squared theta. 16, I'm trying to make sure I am careful here, phi cosine squared theta plus this one we're going to get 16 sine to the fourth phi times sine squared of theta. 16 sine to the fourth of phi times sine squared of theta. So we see we can factor this out from both of those terms, and then we use our favorite trig identity. And then plus, remember this is 1, so there's nothing we need to do with that. And this square gives us 16 cosine squared phi sine squared phi. Just making sure I didn't make any mistakes here one more time, because I don't want to go on and this doesn't simplify nicely as it probably should. All right, let's see. So we factor this out. We'll end up with the our favorite trig identity. So we'll end up with just 16. This is just 16 sine to the fourth of phi right there, and then 16 cosine squared phi and sine squared phi. So we look like we can factor again and actually make this work out nicely. So this equals actually, let's just do this. Let's get any perfect square that's in all three of these. We'll just go ahead and get it out the way, and maybe that'll make things a little bit clearer. So everything has a 16 sine squared phi in it. So that means we can pull that out of everything that's in here and kind of make this a little bit easier. So 16 sine squared phi is in there, 16 sine squared phi, 16 sine squared phi. We can pull it entirely out of the square root, and we'll end up with 4 sine phi on the outside. And then on the inside, we are left with sine squared phi cosine squared theta, sine squared phi cosine squared theta, plus sine squared phi sine squared theta, sine squared phi sine squared theta. And what do we pull out of here? I think we're just left with cosine squared phi here. Yep. All right, so now these two terms just give us sine squared phi and then plus cosine squared phi. So we just end up with this entire thing is 1. So again, factor out a sine squared phi from those two terms, and you end up with sine squared phi times our favorite trig identity, which is 1. So then we end up with a sine squared phi plus cosine squared phi, which again, we use our favorite trig identity and we get 1 there. So this is just 4 sine phi. All right, so that's our magnitude of r sub phi cross r sub theta. Now we need to integrate this. We have to integrate this over some particular region. And they told us that, I lost the question. Sigma is the portion of the sphere that lies above the plane z equals 1. All right, so it's the portion of our sphere that lies above the plane z equals 1. So let's take the plane z equals 1. And if you noticed here this entire time, we've been working in spherical coordinates. So that sphere they gave us, this is rho sine phi cosine theta, rho sine phi sine theta, and then rho cosine phi, our usual x, y, and z from spherical coordinates. So it only makes sense to do the same thing with our z, because we need our everything in terms of phi and theta. So they gave us z equals 1. So z equals 1. But z in spherical coordinates, is rho cosine phi. Now, be careful here not to actually use the variable rho, because there is no variable rho in this problem. Our rho, which is our distance from the origin, is fixed at 2. We're talking about a surface here. We're talking about a sphere. We're not talking about a three-dimensional solid. So when we've been doing triple integrals in the past over some three-dimensional region D, if it happened to be a sphere, then rho would say vary from 0 to 2. But that's the entire sphere being filled in. It's a solid sphere. This is just the surface of a sphere. So our rho does not vary. Our rho stays at the surface of a sphere, which is 2 the entire time. So instead of putting rho cosine phi, we would put 2 cosine phi. So again, rho only varies if we were looking at the inside, a solid sphere, a three-dimensional solid, but we're just looking at the surface of it. So this is 2 cosine phi equals 1. Cosine phi equals 1/2. Cosine phi equals 1/2, which gives us that phi equals, and we'll write our other bounds, our theta and our actual bounds for phi. We'll put those over here. So phi equals, so 1/2 of pi over 3. Not 1/2, sorry. So now let's look at our theta. So we're looking at, remember, so this is the plane, and we're saying that our phi is going to go from, if you imagine the sphere, phi equals 0 will be at the top of the sphere, and then we're going to go down to the plane. Z equals 1, which would be the phi equals pi over 3. Then from there, we need our theta, and theta is going to vary from 0 to 2 pi. I'm actually going to sketch this scenario so we can see just these bounds, so we can see the difference between what we have here and what we have been doing previously when we were working with solid regions. Because phi equals pi over 3, we would think of that as a cone. In actuality, it is a cone. But what's the difference between what we're doing now? And our theta is going to vary between 0 and 2 pi. I'm actually going to use this space for something other than what I intended. So let's look at, I'm just going to actually sketch, I'm going to sketch our whole coordinate system. So let's make a dotted line. We'll make a dotted line of length of, and then put a solid point at the top of that. And we'll say this dotted line has length 2. So we take this dotted line with length 2, and the only part that's going to trace anything out, if I take this and right now it's at an angle of phi equals 0. I take it and I take it down to an angle of pi over 3. Then only thing we get right is right there with the rho being fixed at 2. On the other hand, what we've had in the past is we would have a three-dimensional solid that corresponds to this. And we get something similar over here. The only difference is that, so if that's 2 right there, and then we go over the angle pi over 3, now what we're doing is we're taking a solid line and going over that angle. So this region right here is shaded in. I didn't quite go far enough. And then this will get spun around the z-axis, and that will give us a cone. This one, we take it and we spin it around the z-axis, we don't get a cone. Instead, we would get something that looks like this. And it's not filled in at all. Nothing's shaded in there. The only thing that we actually get is precisely what you see here, with the exception we would get a backside of it as well. So we get that portion of the sphere not shaded in, and the plane at the bottom, the z equals 1, it's an open plane, but it's just a cutoff. This doesn't mean that it's necessarily part of our image, because remember, we're only parametrizing the sphere. There really is no plane down there at the bottom. So that's why this that we're accustomed to seeing over here, which we would spin around and it would give us a cone, usually we'll get this thing. It will give us a cone, of course, with the sphere with the portion of the sphere on top. Now, but this is rho varies from 0 to 2. Our rho is stuck at 2, so we only get the top part of, we just get the part of the sphere, and the bound below it is just the plane, but it's not really part of our image though. So that's just the difference between what we're doing now when we're doing surface area. It is just the surface versus when we were doing something like volume. All right, so now I was going off on my tangent, I forgot. Okay, so now with that, we see our theta also vary from 0 to 2 pi. So now we can set up our integral to find area. Or surface area, excuse me. So now I normally use S, but I'll use sigma since the textbook is using sigma here, just so you at least see me doing it, see it in here, see that symbol they're using 1, sorry. So we have the integral from 0 to 2 pi, and then the integral from 0 to pi over 3 of, what did we get, 4 sine phi. Now, another thing to notice here as well, this is not a triple integral, nor is it an integral where we set it up using spherical coordinates. So we can't, because that's for triple integrals. So you would not put that factor rho squared sine phi in here. That's for triple integrals when you set your region that you're integrating over up using spherical coordinates. But that's not what we did here. This is a surface area problem. It's a double integral, so that's your first hint that there should be no rho squared sine phi in here. And also, because rho is not varying at all, we know that we're not really using spherical coordinates to integrate. We're using spherical coordinates just to parametrize our surface, and that was already given to us. So as we were going through and we were learning those different change of variables, spherical coordinates, cylindrical coordinates, and polar coordinates, I would mention that factor comes in when we set up an integral in those coordinate systems. We didn't set up this integral in those coordinate systems. We just were parametrizing using spherical coordinates. So no rho squared sine phi in here. And these are d phi and d theta. And then you would evaluate the integral. All right, so I'm going to stop this video here and we'll wrap up section 14.9 in the next video.